section 6.2, differential equations, growth and decay. The first thing we talk about here in this section, two things in particular. One is the idea of separation of variable to be able to solve a simple differential equation, or DE. And this comes out of the course called the Elementary Differential Equations, or Introductory Differential Equations. The second thing we talk about is given an application problem, a problem of population growth, to be able to produce that particular formula, and then to apply it to problems where the population is either growing or is either decaying. So first, is that we discuss here is to be able to solve an elementary differential equation by the method separation of variables. This is our goal or objective. Now, first definition is just on a differential equation. You see that differential equation is any equation with a derivative examples of that is dy over dx, could be dx over dy, or with respect to time, dy over dt, dx over dt, dz over dt. And these are first order, could be second order, second derivatives, or third derivatives, whatever, doesn't matter, etc. Or it may contain a differential. Dx by itself, or dy by itself, or dz, dt, ds, dr, d theta, d phi, and so on. So this is our definition of a differential equation. For example, you could have something like 5y prime minus 6x is equal to 0. For this particular problem, has a derivative. This equation has a derivative, so it must be a DE, differential equation. Now, say for example, with the idea of separation of variable, we're going to separate the variables. Here the example is if you have f of y over g of x is equal to dy over dx. So this implies, let me write it a little different here, just for simplicity's sake. What I had there is fine. So this implies if and only if multiply dy on both sides and multiply gx on both sides, then we end up with f of y times dy is equal to g of x times dx. Here the variables are said to be separable in that the terms are alike. So we have like terms there. And also like terms over here. So if we have the like terms from some kind of situation, it may be written different than this, but the goal is, are you able to separate, to get the variables, to get the y's with dy and get the x's with dx? And if you can do that, then you have established the idea of separation of variables, and the variables are said to be separable. Now let's look at some problems here. If you take number 1, for example, you have dy over dx is equal to x plus 3. We're going to get the dx on the right side, multiply dx on both sides. We have dy is equal to x plus 3 dx. So now with this being the case, we can integrate both sides. We have the integral of dy is equal to the integral of x plus 3 dx. This gives us y is equal to 1/2 x squared plus 3x plus some constant. That's the answer. Consider something like number 5. We have y prime is equal to 5x over y. Now you understand that y prime is dy over dx. That's equal to 5x over y. So we multiply y on both sides to get the y over with the dy, and then we multiply dx on both sides to get the 5x and the dx on the same side. So this implies, direct implication, go from left to right or right to left, if and only if. Here we have multiplying y on both sides, y dy is equal to 5x dx. Now we integrate both sides. So this gives us 1/2 y squared is equal to 5/2 x squared plus, let's call it c sub 1. And we'll work on this one to make it look the way we want. Is it okay if I go upstairs? Just put it in. in this box up here. So let's subtract 5/2 x squared on both sides. So we have 1/2 y squared minus 5/2 x squared is equal to c sub 1. Multiply everything by the 2. We end up with y squared minus 5 times x squared is equal to 2 times c sub 1. But c sub 1 is a constant, and 2 times a constant is still a constant. So our answer is y squared minus 5x squared is equal to c, and c represents for us where c is equal to 2 times c sub 1. And that's the answer for number 5. Now let's look at one more here, number 9, and then we'll look at some application problems in terms of growth and decay. Number 9 is 1 plus x squared times y prime is equal, not equal, minus 2xy is equal to 0. Now notice that this is 1 plus x squared times dy over dx minus 2xy is equal to 0. Let's multiply through by the dx. So we have 1 plus x squared dy minus 2xy dx is equal to 0. Now the x's are here, then I have x there, then we have, and that's the dx right here, and then we have the y's. This is dy, I have a y there. And you want to always keep the dx and dy in the numerator, and so divide where you can to make sure that you end up with that. So if that be the case, then the 1 plus x squared needs to be divided all the way through to get the dx with the 1 plus x squared and the x here remaining. And then to leave the dy intact, we need to divide everything by y. So we're going to divide everything by y and divide everything by 1 plus x squared. And what that gives us is 1 over y dy minus 2x all over 1 plus x squared dx is equal to 0. Now with this, you can integrate throughout. This is the integral of 1 over y dy minus the integral of 2x over 1 plus x squared dx equal to the integral of 0 dx. It doesn't matter if we dx dy on 0. You're going to end up with a constant anyway. So now you integrate. So we have the natural log of the absolute value of y minus, now you have to use a u du substitution here. So that u equal to 1 plus x squared. And so du is 2x dx. Well, du picks up the numerator. So this also is the natural log. Basically, you have the integral of du over u. And then that's equal to c sub 1. This guy is just a constant once you integrate. So, if that be the case, I've already integrated this guy. So we have the natural log of the absolute value of y minus, this is the natural log of the absolute value of u, natural log of the absolute value of u, but u is this, 1 plus x squared. That's equal to c sub 1. We can get the natural logs together. This is the natural log of the absolute value of y all over 1 plus x squared equal to c sub 1. Exponentiate both sides is e to the natural log of the absolute value of y over 1 plus x squared is equal to e to the c sub 1. We'll let e to the c sub 1, that's a number, it's a constant, so let that equal to c. And so, now e to the natural log, they're inverses of each other. So the result is this term here, all things positive, so y over 1 plus x squared is equal to c. Well, we've let e to the c sub 1 equal to c. Multiply 1 plus x squared on both sides to get your answer. Y is equal to c times parentheses 1 plus x squared. Now, the last thing, just work one problem. Call it Part B. And the book calls it growth and decay. I have a better term for it, I think. Growth and decay. Each time we deal with growth and decay, it depends on some exponential function. Well, let's see if we can prove that. And we say that by definition that the rate of change of a population is directly proportional to its population at the present time. Mathematical statement. The rate of change denotes derivative. The rate of change of a population is directly proportional to its population at present. Now, the equation that you get from this implies that you can say dy, we usually call it dp, population, with respect to time. This is the rate of change of the population. That's that guy. It's directly proportional, which means that there has to be some kind of constant, k, times the present population. And the population is a function of t. If you go inside and look at it like that. So we just say that is dp over dt is equal to k times p. Now what we do here is separate the variables. P can be equal to y, it doesn't matter. But we just leave it like it is. Separate the variables. This yields for us 1 over p times dp is equal to t, k that is, times dt. So we integrate both sides. Yes. So we integrate. We have the integral of 1 over p dp is equal to k times the integral of dt. This implies that we have now the natural log of the absolute value of p is equal to k times t plus some constant c sub 1. Exponentiate both sides. So this implies that we have e to the natural log of p is equal to e to the kt plus c sub 1. And this is implying the left side is just P is equal to e to the kt times e to the c sub 1. Just use laws of exponents to break that down. Let capital C equal to e to the c sub 1. So we got it. So this implies that P is equal to e to the c sub 1, which is just c, times e to the kt. Now, if k is positive, then P, which is the population, is increasing. If k is less than 0, if k is negative, then P decreases. So, what does that mean? That means here we have decay, and here we have growth. Well, this is the formula that we're going to use, this guy right here, to work the problem. And let's work as a series of problems. We'll just pick number 57, where it says, exercise 57 to 61, the population in millions of a country in 2007, and the expected continuous annual rate of change, K, of the population, are given. You say a whole lot. You know, what is all that? Who cares? Right? Well, comes from the Census Bureau, International Database. You got parts A, B, and C, and let's work number 57. Clear this page out. And again, we're using the population is equal to C times e to the kt. Now, T is time, right? And the population P is given in millions. We're given this country, and in 2007, P is equal to the population 2.3 million. And K, constant proportionality, is negative 0.006. And you don't want to be in that country because they're losing people, right? That negative means that it's the decay. So, part A, find the exponential growth model, P, equal to C times e to the kt for the population by letting T equal to 0, which corresponds to the year 2000. Now, so in 2007, what this means, this implies that T is equal to 7. That's what they're using because you're starting at 2007 for 0. So T is equal to 7 and K is equal to negative 0.06. You plug that into the formula, and they also give you the population. The population is 2.3, and that's million. So we work the formula. P is equal to C times e to the kt. P is 2.3. That's equal to C times e to the k. K is given to be negative 0.006 times T. That's 7. Now, on your calculator, you plug all that in, and basically what you have is that C is equal to 2.3 times e to the positive 0.006 times 7. And I got on my calculator, plugging that in, 2.3987, and they just round that off to 2.3. So what are we saying? We're saying that the formula that we need is P is equal to 2.40 times e to the kt, and k is given, so we don't have to assume that anymore. K is negative 0.006. It's a constant, so it's fixed, times t. The time is changing, of course. This is our formula. So that's what you want for part A. Part B, use the model to predict the population of the country in 2015. So part B, in 2015, the time is equal to 15. That's all you need to plug into this formula here. If you have the calculator, then you get it. So the population is 2.4 times e to the negative 0.006 times 15. And then on my calculator, I get this to come out to be 2.19 million. See how it dropped from in 2000, the population, well, in 2007, the population is 2.3 million. Now here it is in 2015. In 2015, the population is 2.19 million. You want to be in a country where the population is growing? Well, I'm just joking. That doesn't matter. As long as you're not the one who is in that group that's decreasing. Anyway, that's part B. Part C, discuss the relationship between the sign of K and the change in population for the country. Well, since K is negative, notice how we went from 2007, where the population is 2.3 million, to the year 2015, and the population is 2.19 million. So since K is negative, the population is decreasing. Thank you.